Good morning. Today we're going to talk about current, or Ohm's law, and current. So Ohm's law is, you'll normally see it written as V equals IR, but I prefer it as current equals delta V over R, where what this is saying is voltage, which is what we've already talked about, divided by resistance will give you flow. Or, in a more succinct manner, the amount of flow, which is current measured in amps, you can think of it as the flow of charges, number of charges over time will equal the voltage between 2 points divided by resistance. I know, I just kind of threw that out there, but let's look at an example first. So if we have a big mass of positive charges, I know if this is a conductor, then they'd be on the outside, and so I should draw a lot more along the outside, and that's okay. You get the idea. This is just a picture, and we have a mass of negative charges. One more. And then we connect the two by a wire. There we go. Then we're going to have a current, which is the flow of charges, and that's traditionally going to be written as I. I is the current. So we'll have charges. In this case, the representation is we'll have positive charges moving in the positive direction of current, where current is flowing from left to right. And so what Ohm's law says is that you will have the amount of current flow will equal the voltage difference, so the voltage between this charge, this conductor of charges, this reservoir, if you will, and this other clump of negative charges. So we'll have a potential difference between these two, and that will cause the current to flow from the positive to the negative. And we will, since it won't all flow instantly, what we'll take into account is a resistance to flow, which is measured in ohms. And that's represented by this resistor right here. So a resistor opposes flow, opposes electrical flow. So this is where the hydraulic analogy comes in a lot. It's not perfect, but it helps represent a lot of these ideas pretty well. And it's not coincidence that current is, you think of current like a stream or water flowing, and we have electrical current. So another way to think of this is we have a whole bunch of charges right here. That could be a whole bunch of water. So we have a big tank of water. And then we have some sort of pipe. And there'll be some sort of, valve, which offers some sort of resistance to flow. And then we have another tank with very little water in it. Well, you could find the flow of the water from one to the other by looking at the difference in height. So this will create some sort of pressure due to gravity. And this will be, so the flow of water, you could say mass flow rate, would equal the difference in pressure divided by some resistance to flow. In this case, it'd be related to head loss, which you usually see doesn't matter. It's not related to the issue. HL, which is friction within the pipes. And so you have the same situation, or a similar situation, with electricity, where you have a bunch of positive charges and you have a bunch of negative charges, and then you have some resistance to flow in the middle. Now, this right here is a wire. So normally when you see wires drawn in electrical schematics like this, it is assumed that the wire offers zero resistance to flow. Just like if you had a pipe, you'd assume that it has very little resistance to flow, which is not entirely true. Pipes have a significant amount of resistance to flow. And to an extent, wires have resistance to flow as well. It depends on how far you're going is how much it's going to matter. So we have this example, and I'm going to rewrite this slightly. We're going to look at this a little bit different again. So we'll call this side A, which is a whole bunch of positive charges. This is B, whole bunch of negative charges, and the positive charges want to move over to the negative charges. And they'll basically come together and more or less cancel each other out. Now we know in reality, only negative charges exist. So these are a bunch of negative charges, and over here is the absence of negative charges. And so we're going to have electrons moving from left to right. Ooh, from right to left. But by convention, we say that current is positive charges moving in the positive direction. So if we look to the definition of voltage, voltage is the work required to move a positive test charge from infinity to a point. So if we look at the, say, infinities over here, took a test charge, moved it over here, we'd call that VA. Took a test charge, moved from infinity to B, we'd have VB. And so what Ohm's law says, restating exactly what we had up here, is that you'll have current, and I'll make it a small I, doesn't really matter, would be VB A over R, which would be VA minus VB over the resistance to flow. So a quick discussion of notation. There is no clear way of writing the dual notation at the bottom. When you're talking about electrostatics, it's normally written sort of like this, where voltage BA would be voltage A minus voltage B. And that goes back to the definition of voltage being taking a positive test charge from infinity and the work required to move it to a point. In circuits, this will then be normally defined as pretty much opposite of this, where this situation up here would be looked at as VAB, where the first letter written is the more positive charge. So this would be VAB, which would equal VA minus VB. So there is no standard set of notation. You'll say this, you do the notation one way, you do the notation a different way. There's no set way of doing it. Traditionally, when you see it in terms of electricity, VAB will mean that voltage A is the more positive one. And then, because it was written first. And then electrostatics, you normally have the notation where VBA equals VA minus VB, because that basically falls from the math of the integral with regards to work and electric fields. One other point, when we have this resistance to flow, so this resistance to flow, it causes an amount of energy loss. If you think of water flowing through pipes, there's going to be friction. And that would cause, either the pipes moving back and forth, or heat generated, or sound, etc., etc. You'll have some energy loss. And that energy loss for electricity, represented P normally for power, is I squared R. And they're often referred to as I squared R losses. And so what's happening on a bigger level is you have let's say you have a whole bunch of copper, and inside the copper, big copper wire, you have a bunch of copper atoms, and the nucleus is positive, but then you have a whole bunch of negative cloud around it, not drawn to scale. And you have a bunch of electrons which are moving. This is obviously not drawn to scale now. Moving through, and as the electron interacts with basically the electron cloud of the other atom is going to be pushed away. But you still have an electric field generated by these differences in potentials, i.e. the big pool or reservoir of positive or negative charges, which will then cause it to move back on course. So we have an electric field like go in this direction, so electron will move, electric field actually would go in this direction. There we go. So the electron would move opposite the electric field, and the deviation from course, from the straight line course, which will just happen because there's a lot of electrons, not part of the valence electrons for the atoms of whatever the conductor is, that's going to cause some sort of interference. And that interference or deviation from the straight path is what's going to give you more or less these losses or inefficiencies, this resistance and I squared R losses. And if you look at the picture for the resistor, I didn't choose that by random. That's a fairly standard representation of a resistor. Resistor meaning has resistance, electrical resistance. It looks kind of like a coil of wire, which it actually is. It looks more like a cardiogram, EKG, up and down of wire. And one of the ways that they're made is they're kind of actually a coil of wire with like a little ceramic core in the middle, and then commonly. And those of you who know a little bit more might be like, well, that sounds like a solenoid or an inductor. Doesn't that cause, problems? Well, they coil it one way, then they coil it the other way, and the two kind of sort of even out, more or less. Okay, so back to our picture. The general idea with a circuit is it's going to go around. So I'll get rid of all... Oop, didn't mean to get rid of that. Get rid of some of this excess. So the way we normally see a circuit drawn, so we would draw a battery, which we haven't discussed yet, but we will in a sec, a resistor, and then it comes back to the battery. So what the battery represents is we have the reservoir of positive right here. We have the reservoir of negative, jump over, is the small plate. And what happens is, this could be one of the stereotypical examples of a battery would be a lead acid battery. So we have a chemical reaction which releases electrons, and at a reasonably steady rate, and it allows you to store significant amounts of electrons, as opposed to just trying to get a chunk of metal and put an electric charge on it. It's much more efficient to use a chemical reaction. So you could have, we could have blue. So this could be like lead oxide for the top plate, lead, just pure lead for the bottom plate, have sulfuric acid between the two, and that will create a voltage between the two. I think the voltage is like maybe 2 volts or something. And so what you'll see with batteries is they'll stack them together one on top of each other. And without going into too much details, by stacking them onto each other, you then can raise the voltage. So if you have two 2-volt batteries and they're stacked in series, then you'll have a 4-volt battery. And the picture of a battery with a long line, small line, long line, small line, that's kind of sort of what it represents. And traditionally, the long line is the positive side, and then the small sign that looks like a little negative, well, that's the negative side. And that is the idea of a battery. And also by tradition, the current, when it represents positive charges moving in a positive direction. Now in reality, it's the electrons are what flows, and those are negative, and they're flowing in the opposite direction. Yes, true. And science would probably be a lot simpler if we could go back in time and just rewrite everything. But we can't. Can we? Well, you and I probably can't. I don't even know if we should try. I don't know. That is a much deeper conversation than I intended to get into. So, positive charges flowing in the positive direction. These positive charges then counter some resistance. They release some energy in terms of I squared R, where you take the amount of current you have, measured in amps, square it, multiply it by the resistance, measured in ohms, and that's how much power you lose. An example of that would be like a toaster. A toaster, you look into a toaster, not with a fork, just look with your eyes, and you see a little glowing coils. Well, what you have is current flowing through a resistor. I think it's tungsten. And it gives off I squared R losses, which is heat. And then you use that to make your bread nice and toasty. Another thing, so I talked about how resistors are just basically coils of wire. Well, they're coils, but they're thin coils. So one way to think of it would be you have a coil like this is your piece of copper, and then it gets small and then it gets big. Well, this small section here would offer more resistance to flow because you have all this flow which then has to move into small space. And if you think of it as water, current flowing, then it would seem reasonable why you get a resistance to flow, an opposition to flow. One thing you might have heard about is something called the skin effect. And not to get too deep into other topics here, but the skin effect basically has to do with the vast majority of the flow of current is on the outside of a wire. Well, that applies to alternating current. Right now we're talking about direct current, meaning that the current only flows in one direction. Batteries, if you will. If you look at a wall outlet, instead of a battery in the schematic, you would see something kind of like this. And that means that the current would go one way than the other. Well, when you have this alternating current with the, so you basically have your little electrons, or positive charges moving in a positive direction, oscillating back and forth. And that oscillating back and forth causes eddy currents, which means that almost all the flow of current through wires with an alternating source is going to be on the very edge of the wire. That's not true for direct current. Direct current actually uses the whole wire. So if you have a thicker wire, it will do a better job of flow. So that's why, and resistors work for alternating current as well. The skin effect is not. It depends a lot on the frequency. So if you're talking about like 60 hertz, like your wall outlet, then you're going to have like maybe a centimeter. So most wire that you use will be less than a centimeter anyway, so the skin effect is negligible. But going back to resistors, the resistor really can be modeled, and really is for the most part, just a thinner piece of wire. That thinner piece of wire reduces the resistance compared to the thicker wire around it. So now we've talked about how to use a resistor, we're going to talk about how to combine resistors. So let's see here. Boom, 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 boom. Yes. Okay. So when we draw a lot of diagrams, we could draw something kind of like this. So we got a battery. I'm going to call this 9 volt, just for something to have. And we could say this is 3 ohm. And we want to know, let's say, what is the current I flowing. What's the rate that current is flowing? So I, which is dq dt, amount of current flow, is going to equal the voltage over R. And voltage really doesn't exist at a point. It's a comparison between different points. So I'm going to write this as VAB. And I'm going to use the positive side here as A and the negative side here as B. So one of the assumptions with wires in circuit drawings is that wires offer no resistance to flow. So this area right here all has the same voltage. Then there's a voltage drop across the resistor, and then everything along this side would have the same voltage as well. So when I say the voltage, what I really mean is the voltage across the battery here. And you could also write this as maybe V battery. And then this will be the resistance R, since we assume all the resistance is in the resistor. Now there's going to be some resistance in the wires, there's going to be some resistance in the battery, but for an ideal schematic sense, we assume it's all in the resistor. So we want to find the current divided by R, and what we get is 9 volts divided by 3 ohms equals 3 amps. 3 amps. And then we can find the power dissipated as heat due to I squared R losses. So power dissipated due to heat would equal I squared R, which would be 3 squared times 3 ohms. These are amps, these are ohms, and that's 9 times 3, which is 27. And that would be joules per second, because it is power. Also known as 27 watts. Okay, so now the question is, well, that seems to work well, but what if we have multiple resistors? And here are some examples. So we got a couple situations here. So we can have 2 resistors, one after each other. This would be referred to as in series. Delicious crystal light. We can also have resistors in parallel. This is referred to having resistors in parallel. And then we can have some sort of crazy combination of all of them. So the rule we're going to go over first is resistors in series. So the question would be, all right, so we have this situation. Get rid of this guy. Boom. Ooh, blue. I like this blue. Okay, so the question would be, what is I? Or what is the current? Not to current, question mark. And the way that you combine resistors in series is you just add them together. So when I have a problem like this, I try and redraw the circuit to reduce the number of circuits, and we do in terms of equivalent circuits. So resistance equivalent would be R1 plus R2 for series. And the way that I remember that is a resistor is just a coil of wire that doesn't conduct electricity very well. And so you can have something like this as a big coil of wire, and you can just divide it into 2 portions. Where physically this is pretty much the same thing, except they just have a straight piece of wire between them. And so it makes sense to me that if you take a resistor and you have 2 of them right next to each other, you can basically just squish them together and add the 2 resistances together. Because if you look at these 2, R1, R2, and you combine them into an equivalent resistor, this equivalent resistor is going to be R1 plus R2. You can think of this as a person walking through doors. Walking through a door is not that difficult. But if you have thousands of people walking through a relatively small door, it'll become cumbersome. And if you have two doors that are cumbersome, then you're going to have an additive effect for the cumbersomicity between the doors. And so when you have two resistors in series, you add them together. So what we would do then to solve this is I like to redraw the circuits. So, and you don't have to do a very good job redrawing it. Depending on how fluent you are, you can redraw it however you want. So if I did this, I would do something like this. And it's relatively quick. And like, oh, 2 plus 4 equals 6. Bam, got it. Yes. So then we have I equals V over R. A lot of times you'll see Ohm's law and V equals IR. True. This one just feels more intuitive to me because you have the current and you have your pressure causing the current and then your resistance to flow. It seems reasonable. Okay. So current then would be 9 over 6, which is 1.5 amps. Which, okay, seems reasonable. I should have looked at our first one. So if we had just one resistor, then we'd have more current. But since we have two resistors in series, it's providing more resistance to flow, and so we have a lower current than if we had just one resistor or the other. Seem reasonable so far? Okay. So now if we have two resistors, we also have a rule for equivalent resistance. So the way it works is 1 over equivalent resistance is 1 over R1 plus 1 over R2. And I only write R1 and R2 over here, but we can add in 1 over R3 and then go on forever as desired. Excuse me. Went for a run this morning and I'm still a little, my throat's a little, That's okay. It's good for the soul. Probably the body too, I would hope. Okay. So same idea here. We're going to redraw this again. And you can use whatever level of detail you want in life. The more you do, more problems like this you do, the more fluent you'll get. And when you're talking about many resistors, you don't have that much time. And it can take a while to redraw every single diagram. But redrawing it, I think, helps keep things straight in your mind. So we'll do 1/2 plus 1/4. That's 1 over 2 and 1 over 4 equals 1 over R equivalent, which equals, and I'm going to do this part, so it'll be 2 over 4 plus 1 over 4 equals 3 over 4. Therefore, R equivalent would equal 4/3. So I write up here 4/3 ohms. One thing to note is 4/3 is less than 2 and less than 4. So it'll be less than either of them. If you go back to the example of a whole bunch of people trying to get into a building, if you have two doors side by side, it'd be easier for people to get in than if it's either just one door or the other door. Make sense? And that's a good sanity check, is after you do your math, you should get a number that's smaller than either of them. If for some reason I got a number like 3 or 7, then I'd be like, no, that can't possibly be correct, because it would have to be less than either of them. Because having two doors open is easier than having solely one door open by itself. Okay, so I equals V over R, which equals still 9 volts divided by 4/3 fractions. Multiplied by the reciprocal, 27 over 4. Ooh. That's what, like 6 something? 6.75? 6 3/4. Because 7 times 4 is 28. Okay. So let's see how these compared. So, amps. So between these two examples, this is saying that if we have two resistors in parallel, then we'd have a much higher current than if we had two resistors in series. And That is true. And it makes sense too, because again, if you use the idea of like a bunch of people trying to get into a building, having two doors where they have to go through one door to get through the other door is going to be significantly slower than if they have two doors that are parallel and people can just enter through both doors. So it makes sense that we'd have a greater flow of charges, just like we would have a greater flow of people. Okay, I'm going to go with that. So now, bam, the crazy example. This example actually isn't all that crazy. You can get pretty... So, but I just want to show you how this would... how you would go through a problem that's a little bit more complicated. Not complicated, a little bit more intensive maybe? I don't know. So, the way I would do this, I would draw it up again, and I'd be like, all right, 1/2 plus 1/4 equals 2/4 plus 1/4, which equals 3/4, which implies that R equivalent equals 4/3. So I would do 4/3. Then I draw the other resistor again with a 3. And then I would draw another resistor down here. And then for this one, then I would do, okay, so we have 1/2 plus 1/1 plus 1/3. Looks like we're going to go for 6 as the common denominator. So we'd have 3 plus 6 plus 2/6, which equals 11/6, which implies that the R equivalent would be 11/6, which is a little bit less than, nope, that can't be right. Can't be right. Did I mess something up? I probably messed something up. Ah, I did mess something up. 6/11. Haha. So 6/11, and the reason I knew I messed something up is because 11/6 is bigger than 1. And the equivalent resistance that I would get would have to be less than any of the individuals. And 6/11, which is basically a half, plus a little bit, is less than all of them individually. So 6/11 is reasonable. 6/11 ohms. And so now I have 3 resistors in series. I would then rewrite this again. Battery, resistor, and back. And this would be 4/3 plus 3 plus 6/11. So we're going to use, I guess, 33 as our common denominator. So we'd have 44 plus 99 plus 18/33, which is, I don't know, 143 plus 18, which is, make a little arrow there, 161/33, which is, I don't know, 5. So we have about 5-ish ohms. Yeah, about 5. 161/33. So then our current, 9 volts, current equals 160, let's see, 9/1 volts. I put the 1 in there because I know since the resistance is a fraction, I'm going to have to multiply by the reciprocal. 161/33. And make sure that 5 is bigger than 4/3, 3, yep. And so since it's in series, the total resistance should be more than any of the individual resistors. So it's true. At least not entirely wrong. So we have 9/1 times 33/161. Yep, I'm not going to do that in my head. I'm going to be like, 2. Is it about 2? About 1.75-ish. Fine, I'll do it for real. 9, 33, and 161. 9 times 33 divided by 161. And we get 1.85. 1.84. Okay. 1.84 amps. There we go. And that's how you do a longer problem with equivalent resistors. This is a lot of writing. Okay, now we're going to switch tasks real quick and look at the sort of problems that you would actually encounter on the AP exam. All these sort of things should be sort of taken for granted. And so, ooh, I do like that picture though. I might leave that part up. Okay, let's look at another kind of problem that we would get. Okay, so here is a kind of a free response type question that you might get for an AP exam. So we're talking about a physics student who wishes to measure the resistivity. I don't think I've even defined that yet. I will in a sec. A slightly conductive paper that has a thickness of that. The student cuts a sheet of the conductive paper into strips with a width of this and varying lengths, making 5 resistors labeled R1 through R5. Use an ohm meter to measure the resistance. The student measures the resistance of each strip as shown above. The data are recorded below. Data is always one of those funny words because it feels like it should be singular, but it's actually plural. Datum? Is that a single data? Okay. So resistivity is I think they normally use the symbol rho, which bothers me. And it is the resistance per unit length. And so, and the units for this is actually going to be ohms meters. And so, to think of this conceptually, you have your big piece of copper wire. And what you're going to do is you're going to have the resistance, find the resistance times the resistance of the whole piece times the cross section divided by the length. And so the idea with the cross section here is if you had a thick piece of copper, it would have a different resistance of different resistivity than a thin piece of copper. So resistivity isn't unique to a material like copper, silver, gold, or iron or whatnot. Resistivity has to do with the cross-sectional area as well. But then they normalize it by length. So the idea is if you have a whole bunch of copper wire of a gauge being a thickness of the copper wire, you would have a resistivity for that spool of wire, but you wouldn't have a resistivity for copper in general. So let's see here. That's why they give you the thickness of the paper. So let's see here. Using the grid below, plot a linear graph of the data points for which resistivity of the paper can be determined. Include all labors. Okay, so we're going to try and use the slope to find the resistivity. Yep, linear graph, which basically means you should be thinking slope. So the equation for resistivity will be resistance, which I think we're given. Are we given the resistance? We have an ohm meter, so yep, given resistance. And then multiply by cross section. And then we'll divide by length. Yep, length of each piece of paper. And this is rho, the resistivity. I'm just going to write resistivity because I hate using rho. When I think of rho, I think of density. So rho is mass over volume, or a small amount of mass for a small amount of volume, or like a small amount of charge for a small amount of volume. I like things with rho to deal with volume. Personal animosity in life. Okay, so we want to set it up with this on top because we want a rise over run situation. Rise over run. And we know that this is the equation for resistivity. One way to know that, or a dummy check to make sure that you're not completely wrong, is you know that resistivity is measured in ohm meters. So you have here ohms, you have cross-section will be meters squared, and then the length will be in meters, and one of the meters will cancel, and you'll have ohm meters. Yep, they don't give you the units for resistivity, so you really can't use that as a fallback. Okay. But it's good to think of it as a resistivity as a linear, a resistance per unit length. So let's see here. So we need to find the cross section. Cross section. Has a thickness of, so this is a piece of paper, has a thickness of 10 to the negative fourth, and it has a 2 times 10 to the negative second as the width. And so the cross section would be the two multiplied by each other, so it would be 2 times 10 to the negative 6 square meters. Resistance is 0.8 times 10 to the fifth times 2 times 10 to the negative sixth. And then that would be 1.6 times 10 to the negative 1, which equal 0.16. Okay. And then I'm going to do that for all of them. It'll be a little bit tedious, so I'm just going to zip right through it. So I have up here where I have the resistance multiplied by the cross-sectional area. And now what I'm going to do is I'm going to take that and I'm going to put that along the y-axis because I have my rise over run. I want that to be the rise portion. And then the run will just be the meters, and I will graph it out. Again, a little bit tedious, so I'm just going to zip right through it. And so here we have the points graphed on our line. So now we'll do a, yeesh, that is not a happy straight line. There we go. We'll do a line of best fit, or a line of slightly adequate fit. And this gives us our slope. Now, ideally, you'd use some sort of regression formula, put them in your calculator. Now, I'm just going to use the first one and the last point, and then just do y2. So, delta m equals y2 minus y1 over x2 minus x1. Since they all seem to line up kind of, sort of okay, I'm going to do 0.16, and that's ohms meters squared, over length 0.02 meters. And if I was a better person, I would do that in my head. Oh, wait a second. I forgot to do the whole subtraction part. Slope of line. Yeah. Okay, 0.16. Actually, here, so let's do y2, which would be 0.88 minus 0.16 all over 0.1 minus 0.02. There we go. And then using Wolfram alpha, let's see, 0.8 quantity 0.88 minus 0.16 divided by quantity. Let's go 0.1 minus 0.02, 0.1 minus 0.02, and we get, bum, 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 finally after all of our work, 9. Feels like I should have done that in my head. And so we get the resistivity is 9 ohms meter. So to backtrack, I know this felt like a little bit tedious, and it kind of is. And you're given about 15 minutes for this kind of problem, and for this section of the problem, you probably only get maybe like 5 minutes, so you have to move pretty quick. So what it asked was, all right, so we need to know the definition of resistivity, which you just have to memorize. Resistance times cross-section over length. And you know that it's going to be ohms times meters will be the units for resistivity. And so we graphed all the resistances times cross-sections on the y-axis because we're going to look for the rise of a run. And then we did the length on the x-axis, plotted them, and then we just took 2 points and did y2 minus y1, x2 minus x1. And plotting them was basically just to show that they show up in a line, and therefore we can use the slope method. And then we do all that again, using the graph, calculate the resistivity of the paper. There we go. And we get final answer of 9 ohms meter. So, yep, that's an example of what we would do with resistivity. So that's going to be all for this one. I'll go over some more examples next time, and we'll work through pretty much a bazillion problems. Appreciate it. I will see you next time.